talk will be recorded. So if you have questions, you can either write in the chat or please just unmute yourself and ask questions. So today I'm very happy to announce our speaker, Shoham Letzter. She did her PhD in 2015 with Bela Bolobash in Cambridge. Then she had postdoc positions in Cambridge and ETH. And then she won Royal Society University Research Fellowship and a lectureship at University College London. And she works in extremal and probabilistic combinatorics and many other questions. And today she's going to talk about Size-Ramsey numbers of powers of tight path, please.
Okay, thank you, Oleg. Thank you for the invitation and thank you all for coming. So as Oleg said, please feel free to ask questions. I don't always notice the chat, so if there's something on the chat, maybe someone can alert me. Okay, so this talk is joint work with Alexey Pokrovskiy, who also just started a lectureship in UCL, and Liana Yepremyan from LSE. And I'll be talking about Size-Ramsey numbers of powers of tight paths. So just generally speaking, this is a talk about Ramsey theory, so I might as well start by introducing Ramsey numbers. Okay, so I will use this notation G arrows H if in every red-blue coloring of the edges of G, there is a monochromatic copy of H, namely a fully red copy of H or a fully blue copy of H. So for example, K5 does not arrow K3 because here is a red-blue coloring of a K5 without a red triangle or a blue triangle. But as most of you probably know, K6 does arrow K3. Okay, now we define the Ramsey number, R of H of a graph H, to be the minimum n such that the complete graph on n vertices arrows H. So for example, here, we can easily see that the Ramsey number of a triangle is 3. And an equivalent way of looking at the Ramsey number, which will be useful in the next slide to have in mind, is the following definition. The Ramsey number of H is the minimum number of vertices in a graph G that arrows H. Okay, so here is an early Ramsey type result by Geranger and Garfash, which is kind of a pretty rare example of a family of graphs for which the Ramsey number is known precisely. So it says that the Ramsey number of a path of length n is this expression, which is roughly 3n/2. And here you can see the proof of the lower bound. So you can see that in this coloring, there is no blue path of length n because there isn't enough space in this left blob. And also there is no long enough red path because in any red path, like every other vertex would have to come from this small blob. And again, there aren't enough of them. Okay. So this is nice. So in a sense, it tells us that you can find monochromatic path quite efficiently. So you only need, for a path of length n, you only need a bit more vertices, so 3n/2. However, if you kind of want to think about it a bit more, then you see that this graph has n² edges. So in some sense, it's like, in terms of edges, it's not super efficient. So with this motivation in mind, Erdős, Fodry, Russo, and Schopp suggested to kind of try to somehow refine our understanding of Ramsey graphs or of graphs that arrow another graph. So they made the following definition of the Size-Ramsey number, R hat of H of a graph H, to be the minimum number of edges in a graph G that arrows H. So in the previous slide, we had the Ramsey number was the minimum number of vertices in a graph that arrows H. And here we'll be looking at the minimum number of edges. Okay, and then going back to this example, so so we see that the Size-Ramsey number of a path is at most n², but that is perhaps inefficient. So Erdős asked, well, is it true that you can do better than n squared? So little o of n squared. But he also kind of thought that maybe going as far as linear in n is just hoping for too much. But turned out, perhaps surprisingly at the time, that you could actually do, you could go down to linear. So the Size-Ramsey number of a path of length n is linear in n. And okay, this was maybe surprising at the time, but now it's kind of pretty easy using if you know, or if you use the right tools. So I can ask, well, about for more precise bounds. So what is the right constant here? And here are the best known bounds. So the Size-Ramsey number of a path of length n lies somewhere between 3.75 times n and 74 times n. And this 3.75 may not look very impressive because, well, 2n is a trivial bound, and this is not even twice that bound, but it's actually really quite hard to prove lower bounds on Size-Ramsey numbers. So this requires some effort. Okay, so this is what I wanted to say about the Size-Ramsey number of a path. Now, okay, we essentially know what it is up to the constant. So maybe, I mean, can we say more, or can we extend this result? And I will show you a few ways in which we indeed can do that. So one result of the type is the following. By this group of people, they show that the Size-Ramsey number of any fixed power of a path of length n is again linear in n. So previously we saw that the Size-Ramsey number of a path is linear, and here we see that also the power. So just in case you're unfamiliar, the nth power of a graph H, I can hear my echo, somebody maybe is unmuted. So yeah, so the nth power of a graph H is a graph on the same vertex set as the vertex set of H, with edges that are pairs of vertices at distance at most L from each other. So for example, here is a drawing of P6, so the path of on 6 vertices cubed. So here is like P6. Oops. So these guys form my P6, and then to form the third power, we connect every 2 vertices that are at distance 2. So these are these edges, and at distance 3, these edges. Good. Yeah, so this was one generalization of what we had in the of the fact that the Size-Ramsey number of a path is linear. Now, another way to generalize is to say, well, why just look at 2 colors? Let's look at more colors. So here's the definition, should be kind of natural. So instead of 2 colors, I now want to look at S colors. So I write G S arrows H if in every S coloring of the edges of G, there is a monochromatic copy of H, and the S color Size-Ramsey number R hat sub S of H is the minimum number of edges in a graph G that S arrows H. Okay, and the kind of further generalization of, I guess, this result is that, in fact, you can say the same thing for arbitrarily many colors. So the S color Size-Ramsey number of an nth power of the path is linear. Good. So this was powers of path, and then, well, you might want to extend this to other graphs. So here is, instead of path, we look at bounded degree trees. So here's a result that, again, generalizes what we had in the previous slide. It says that given a tree which is bounded degree, the Size-Ramsey number of any fixed power of it is linear. And similarly to what we had before, shortly after this result appears, the same was proved for an arbitrary number of colors. Okay, so now you may ask, well, maybe like trees is too restrictive. Maybe we could just look at, I should say that if the degree is unbounded, then essentially the Size-Ramsey number would not be linear in most reasonable cases, I think. So if we're looking at if we want to look at graphs whose Size-Ramsey number is linear, then we should look at bounded degree graphs. So one could ask, well, is this true for any bounded degree graph? The answer is no. It was actually a conjecture of Beck, but nevertheless, the answer is no. And this is, again, like it's hard to prove lower bounds on Size-Ramsey numbers, but nevertheless, a result of Rödl and Semrady gives a construction of a family of graphs whose maximum degree is 3, but whose Size-Ramsey number is not linear. So it's at least n times some log n to a small power. Okay, so we can do trees, we can do powers of trees. We cannot do any bounded degree graph. So can we say anything about bounded degree graphs? Turns out that we can say something, and the way to say something kind of meaningful if we want to go towards a linear Size-Ramsey number is by looking at subdivisions. So we'll define the Q subdivision of a graph F to be the graph obtained from F by replacing each edge by a path of length Q. So it looks something like this. Here's my graph F, and a 3 subdivision of F is obtained by essentially just dividing each edge into 3 parts by putting 2 new vertices on each edge. So this is the Q subdivision. And a couple of recent results by Dragonich, Krivelevich, and Nenetov show that that taking Q subdivisions of a bounded degree graph kind of pushes us towards a small Size-Ramsey number. So the first result goes as follows: given a graph H which has bounded degree, if we take the Q subdivision of it, then the Size-Ramsey number of the result is the number of vertices in H to this power 1 plus 1 over Q. So kind of the larger Q is, the closer to linear we get. We don't quite get to linear, but quite close. However, if we do want to genuinely get to a linear number, then what we need to do, or using the results, what we can do is take constant times log n subdivision. Okay, so now let's switch gears a little bit and let's talk about hypergraphs. So somewhat surprisingly, until it was only recently that people started considering Size-Ramsey numbers of hypergraphs. So this was first done by Dudek, Fleur, Mubayi, and Rödl a few years ago. So I will not write the definitions again because they will be essentially the same thing. So previously we defined G arrows S. We said that G S arrows H if in every S coloring of G there is a monochromatic copy of H. So previously we defined it for graphs, but if you think about these as hypergraphs, the definition will be the same. And so similarly, you get the definition of the size S-scalar Size-Ramsey number of hypergraph. Good. And now we're still in the theme where we're trying to find examples of hypergraphs or graphs whose Size-Ramsey number is linear. And the first graph that we looked at was the path, so we might as well try to generalize that. And the way we will do that is by looking at the tight path. So the tight R uniform path, denoted like this, P sub n brackets R, on n vertices is the R uniform graph on vertices u1 up to un, whose edges are sets of R consecutive vertices. So for example, here we have the 3 uniform path on 7 vertices, and well, the vertices are arranged in a line, and we put an edge for every 3 consecutive ones. So this is the tight path. And these guys will ask, is it true that the Size-Ramsey number of the R uniform path is linear? So the best general result before I work was the following, bound by Lu and Wang, who showed that the Size-Ramsey number of the R uniform path on n vertices is this expression, which is n log n to the r over 2. So I should say that n to the r is essentially trivial by results on the Ramsey number of these tight paths. So they kind of halve the exponent essentially. And then recently with Hankwaya, Kawamota, and Partzik, we answered this question affirmatively for the first case, for r equals 3. Okay, so now I want to talk about our results. So we have, in our paper, we state a kind of general thing, but here I'll just put a few consequences. So first, let me make a definition. So it will define the lth power of a tight path to be the graph on vertices u1 up to un, whose edges are subsets of size r of any r plus l minus 1 consecutive vertices. So just a sanity check, if we put L equals 1, then this just recovers the definition of a tight path. So this just tells us that every L consecutive vertices form an edge. And let's look at an example. When R equals 3 and L equals 2, then our edges are any 3 vertices that are contained in an interval of length 4. So for example, things like this could be an edge and things like this could be an edge. Right, so here's kind of the first main result. It says that for every fixed R, S, and L, the S-scalar Size-Ramsey number of the lth power of an R uniform tight path is linear in the number of vertices. Okay, so this, I guess, generalizes the results about the linearity of the Size-Ramsey number of powers of path. Now we have a kind of similar generalization for trees, but statement maybe a little bit less natural. So here we show that for every tree, so this is just a graph on n vertices whose degree is bounded. Well, I want to look at the corresponding hypergraph, so I'm going to take the R uniform hypergraph that is obtained by taking all R cliques in the lth power of T. Right, so again, I don't know how natural this looks, but doing this, making an R uniform hypergraph from a graph in this way is something that we'll do later, so I guess it's useful to see. And also I should say that we can prove something similar for hypergraph trees. I just didn't want to include the definitions that we need for that. So anyway, this generalizes the results about powers of trees. And finally, we can also generalize like the second result about subdivisions, about so-called long subdivisions. So it says the following. It says that given a graph H on n vertices, which is the L subdivision of a graph with bounded degree, where L is at least some constant times log n. So I guess you take a bounded degree graph, you subdivide each edge by at least this many vertices, and then if you take the lth power of this thing, then there you get a graph whose Size-Ramsey number is linear, whose S-scalar Size-Ramsey number is linear. Okay, so I will, in my talk, I will focus just on this result. And to start, I will talk a little bit about what happens in the previous proof. So in previous proofs that show linearity of Size-Ramsey number of various things. So how should we start? Well, we want to show that something has linear Size-Ramsey number. Well, what does it mean? How do we do that? Well, by the definition, what we have to do is we have to find a graph which has linearly many edges and whose every S-edge coloring results in a monochromatic copy of whatever graph I'm trying to find. So the way to start these proofs is to decide, well, which host graph do I want to have? So we do the following. We take G to be an expander well, we need obviously at least n vertices, and we cannot take much more, so we take some large constant times n vertices. And we also assume that the expander has bounded degree. Now for us, expansion will mean that there is an edge between every two large sets. Not really important, not going to feature, but various other kind of stronger notions of expansion were used previously as well. And I guess I should remark that such an expander exists. Just take a random graph and maybe delete large degree vertices. Right, so I have my expander, and now I'm going to tweak it a bit. So I'm going to take a power of the expander, and I'm going to take a complete blow up of this power. So again, let's maybe look at this example. Say, pretend that this is my expander G, then I want to take a power. So this here, I drew the square of this G. And then I want to take the complete blow up. So I replace each vertex by this clique, and I join all edges between two cliques if there is an edge in the corresponding power of G, and otherwise I don't put any edges. Okay, so this will be my host graph for for I guess most of the talk, or something slightly similar. Yeah.
So B is a number or a set? I'm confused.
Oh, yeah, sorry. This is just a number. So I will, I will use B for the number, but also I will denote P of U to be the blob at U.
Yeah, thank you.
Okay. Right. So so very kind of general overview of previous proofs. What we do, or what I did, is to fix an take my graph, fix an S coloring of it. Now notice that because each blob is pretty large, by just Ramsey's theorem, there is a largish monochromatic subclique. So let's denote the subclique, this monochromatic subclique, by B prime of U. Right, and then without loss of generality, let's say that the most popular color for the clique, for these subcliques, is blue. So we're going to just ignore everything else except for the vertices that are in these blue subcliques. And then I'm going to hope that there are enough edges in between to sort of join up these subcliques. But if not, I need to do something else. If not, I need to somehow say, well, there cannot be many blue edges in some way. And then I try to find, if I have just two colors, then this is a bit easier. Then I just say, okay, there are not that many blue edges, so there are many red edges, so I can find my thing. Otherwise, you may need to do some kind of iteration. But anyway, this is at least, let's say, the first step in most previous proofs. Okay, so what is different for us? Well, first we need to have a hypergraph. So we take, again, this hypergraph that obtained from this graph by just letting the edges be the R cliques in this graph. Right, so just to visualize this, in gray here, you have this complete blow up of my power of G, and my edges will be the triangles in the gray graph. So let's say we can have these triangles with 3 vertices in one blob, or 2 in one blob and 1 in another, and so on. So this is how my host graph will look like. And now, right, so what previous results did before, they said, okay, we can find something monochromatic, but actually you can do quite a lot more. So this is our first new ingredient, and then people did not notice this before us. Right, so it says the following: given a hypergraph H, which has bounded degree, let's look at an S coloring of the complete blow up of H by B vertices. So this is essentially the setup that I have here. Then I claim this lemma tells me that in each of the blobs of H, there is a largish subblob, such that if we restrict just to the subblobs, then any two edges that look the same, so they have the same intersection size with each subblob, have so every two vertices, every two edges like this, have the same color. So maybe easier to visualize with a picture. So what it says here is that after we restrict to these sublobes, we get the following. We get that if we look at one blob, then all the edges within that blob have the same color. But also if we look at two blobs that are joined, then any edge that has two vertices in one blob and one and the other have the same color. And similarly, I can have this the same thing for edges that have one vertex in one particular blob, one vertex in another, and the last vertex in the third blob. Okay. Yeah, so I don't really want to go into the proof of this, but it's not hard. You just use a Ramsey type result for each kind of type of an edge, and you use the fact that the degree is bounded to say that every blob participates in only boundedly many types of edges, and so you won't end up shrinking too much. Okay, right, so this is our new ingredient. So again, just to emphasize, previously what people did was just to guarantee that we have something like this. All of these have the same color, but they did not look at edges like this, even though it turns out to be quite useful. So let's see one way in which this is useful. So this is again the same lemma. And what I'm trying to show is that the scalar Size-Ramsey number of this Lth power of a tight path is linear, right? So what I claim here is that actually it's essentially enough to, instead of find a tight path, to find an Lth power of a tight path, to find an Lth power of a tight walk, as long as I don't have too many repetitions. So let's repeat this. I claim that it's enough to find our uniform hypergraph H, which has not too many edges and has bounded maximum degree, whose every S coloring has an Lth power of a tight walk on n vertices, where each vertex repeats not too many times. So to see why this is true, it's quite easy. Suppose that this is the H that I am guaranteed here. So this will be just, I will draw graphs here because it's easier to draw. Okay, so this is my H that I am trying to find. So suppose that I manage to find this. I want to show that I can find this tight path. So here I can find a tight walk. Here I want to be able to find a tight path. So now by this lemma, essentially I can assume that this lower graph, which is a complete blow up of the upper thing, I can assume that it looks kind of monochromatic like this after I deleted some vertices. So I can assume that each blob is monochromatic and all edges between any two blobs have the same color. This gives me kind of naturally an auxiliary coloring for H. So I color this edge red because these edges were all red, etc. Now, my property of H guaranteed that I could find a long walk or a long power of walk, but for this picture, a long walk in H. And then the point is that I can lift this to a long path in the blow up, because basically every vertex has many copies. So for example, this vertex here is used twice. So just for each time it is used, use a different copy. So point is, yeah, here all the vertices are just copies of each other. So I can compensate for using the same vertex a few times. Right, so this already looks, I would say, quite promising. Like at the very least, it helps you avoid some technicalities that you may have had to deal with before. Right, and now my plan is to show you how our proof would go if we were proving just the R equals 2 case. So this is, in other words, we're now reproving the powers of path result. So this is not new, but this should help to understand my main proof, assuming I managed to get there. So again, this was my host graph, so I consider an S coloring of it. Then by the Ramsey lemma from the previous slide, I can assume again that the picture is something like this. So after maybe removing some stuff from each blob, I can assume that vertices in each blob are twins, look the same. Okay, and now I want to define an auxiliary coloring of this power of G. So I will color an edge UV by color C. If there is a short C-colored L power of a path that starts with L vertices in the blob of U and ends with L vertices in the blob of V. So for example, I put the red edge here because I can take L vertices here, and this would give me a red Lth power of a path. And similarly, this edge is orange because I can take L vertices here, then L vertices here, then L vertices here, and again I get like short orange L power path from here to here. And I may fail to do this in all colors, and then if that is the case, then I put a gray edge. Right. So I have my auxiliary coloring, and now let's assume that we're kind of lucky and we found a long monochromatic non-gray path in my auxiliary coloring. So suppose that U1 up to UN is the red path in the auxiliary coloring. This means that we have a picture like this. We have we have my U1 up to UN, U5 here. And each of them stands for a blob in my kind of in my original graph. And the meaning of a red edge between U1 and U2 is that there is something like this. I can start with some L vertices here, end with L vertices here, and have some short way of walking between the two. And similarly between U2 and U3, and so on. But now I recall that vertices in U2 are all twins of each other. So I can just take these guys and replace them by these guys and kind of identifying the end vertices here, similarly here. And from just a collection of disjointed L powers of path, we get this long L power of a walk. So it's a walk because some of the inner vertices of Q1 may be reused by Q2, etc. But it's not hard to see that no vertex will repeat too much. And so this will give me the walk that I claimed was enough. So if I manage to find a long monochromatic non-gray path in my auxiliary coloring, then I'm happy. So what happens if not? If not, well, claim that instead we will be able to find many largish gray cliques that cover almost everything. So we look something like this in the auxiliary coloring. And now remember again that each blob stands for, each vertex stands for a blob and in the blow up. So it will look something like this. I will have these sort of two-level blobs, and because there is a gray edge between any two, this means that there is no short monochromatic L power of a path between any two small blobs in a medium blob. Okay, so how can we use this? Claim that by, again, applying some kind of Ramsey argument. I won't say exactly how, but essentially I can assume that every blob looks like this. So every blob within every of these like two-level blobs, all the small ones, I may assume that all the small ones have the same color, and all edges between them have also the same color, but these two colors have to be distinct, because if everything here was blue, then I would have a way to walk from one small blue blob to the other. Right. And I guess that's important, but I can also assume that the edges between any two-level blobs have the same color. Okay, so this was, in the first case, I found a long monochromatic path and I was happy. Otherwise, I found these cliques, which essentially tell us that we have many of this kind of structure. And now what I'm going to do is just repeat. So again, define an auxiliary coloring, this time depending on the behavior of any two blobs like this. And what will happen is that either I will again find I find a long monochromatic path in my auxiliary coloring, which will translate into a monochromatic S power of a walk on and vertices with few repetitions. Or I get from two-level blobs, I get three-level blobs, which again have this property that I cannot walk in a short monochromatic way between any two small blobs or any two medium blobs, etc. And then again, I can repeat the Ramsey reasoning to be able to assume that all small blobs have the same color, all edges between small blobs but in the same medium blob have the same color, and all edges between medium blobs also have the same color. And again, because of this text here, we will find that these colors have to all be distinct. But that just means that, sorry?
I wanted to ask, but your like higher level blobs, they're not clique, they're just connected graphs, or no? Or
they are cliques, like everything is kind of like a small constant. So, right, because the way I generated them in the first step, I had these gray cliques. So that means in particular that they are cliques in the original graph. Like each vertex stands for a clique, and each gray edge stands for a complete bipartite graph between them.
But between them, how do you know there are edges between them?
Oh, because I put a gray edge only whenever there is an edge. Like if we go back a few slides, so yes, I put a gray edge only when there are edges between the two blobs, but there is no walk. So here there is no edge, and then there are no edges here, and then I put no gray edges. So gray edge means that I cannot walk between the two things, but there are edges. So.
So in terms of n, they're just constant size cliques, right?
Yeah.
Yes, I see.
Yeah.
Thank you.
Okay, so we saw after 3 iterations that either I'm happy, like I managed to find what I looked for, or I get this 3-level blobs that has used 3 colors. Similarly, after S+1 iterations, either I'm happy or I find an S+1 level thing with S+1 colors, but there are no S+1 colors, and so yeah, so I won't have that bad outcome. So I will eventually, after at most S+1 iterations, find what I want. Good. So this was with only a little bit of lying the proof, our proof technique, but for the powers of path question. And now what I want to do is to show you how essentially the same ideas can be used for the general powers of tight path case. Okay, but it's kind of, we will want to use these leveled blobs, but it's a bit harder to kind of explain, I guess, what a type of an edge is. And so for that, we use the notion of ordered trees. So a bit of an ad hoc notion. So the definition goes as follows. A DRA ordered tree of height h is a complete DRA tree of height h, along with an ordering of its leaves that comes from a planar drawing. Okay, so a complete DRA tree of height h is just a rooted tree such that the root has the children, each of the children have the children, etc., up to level h, where everything, where they don't have any children. So this is my tree, and what makes it ordered is that, well, imposing an ordering of the leaves that looks nice. And by looks nice, I mean, well, looks something like this. So here is an ordered tree of height 3. And the ordering is just take the leaves from left to right. This for me would be a kind of nice ordering, and a not nice ordering is an ordering that comes from a kind of scrambled drawing of my tree. So this is not a tree with this ordering, is not an ordered tree. Okay. Yeah, so it's actually kind of hard to explain what this means in a very rigorous way, but hopefully it's clear from the picture. Good. And now why do I bother with these ordered trees? Well, because they are useful in modeling age-level blobs with an ordering of the vertices. So here is a 3-level blob, and I claim that it corresponds to this tree. So really, each vertex in my level blob corresponds to 1 leaf, and 3 leaves that are in the same, have the same parent, are in the same small blob. Any kind of 9 leaves that have the same grandparent are in the same medium blob, etc. And to talk about a type of set of leaves, so really everything, I mean, in the real world, everything just happens in the leaves, like these vertices are sort of just auxiliary vertices, I guess. So to be able to do that, I will use the correspondence between sets of leaves and ordered subtrees with T leaves. So for example, if I look at this set of 3 leaves, then I will often, instead of talking about the set of leaves, I will talk about the corresponding tree. So the minimal subtree that has exactly these leaves. Good. And now my plan becomes the following. So again, I will do a sort of iterative procedure where in step J, what I want to find is a large set of vertices in my expander graph G. So here's my large set of vertices. And for each vertex in G, there is a tree rooted at that vertex. So the tree will be Tj of U. It's a DJRE ordered tree of height J. So we're kind of going to increase J step by step. And as J increases, like the degree of the tree will decrease, I guess, but the height will increase. And the increased height kind of corresponds to increasing the level of the blob, so increasing the complexity of the structure that we have. Right, and finally we'll have a similar sort of property that we had for the level blob. So this kind of corresponds to these gray edges. So what we assume is that there is no short monochromatic nth power of a tight path that starts and ends at disjoint sets of leaves that correspond to isomorphic ordered trees. Okay, so I expect this to not be super clear, but also I didn't fully explain kind of where these things live, but essentially these leaves will be like complete graphs and they will correspond to some actual edges of the graph that I was looking at. And this again says something like, I cannot walk from 2 trees that look the same. Right, so this is my plan. And what I should show you, I guess, in the next few slides is that, well, firstly, if I am a step J, either I can find what I want, either I can find my power of a tight walk, or I can move to the next step. So that's one thing that I should show you. And also I should tell you why at some point, well, this process will end, so it cannot run forever. Right. So this is the sort of Ramsey type lemma that we used, but for trees. So it says essentially if you start with a ordered DRE tree of height h, where D is large, then for every S coloring of the sets are sets of leaves, I can find a smaller tree, but still large, so a DRA subtree, T prime, of height h, such that in T prime, are sets of leaves that correspond to the same tree, have the same color. Okay, so I start with this like very massive or tree of height h, but with very massive number of children per vertex. And I claim that I can trim it to get something like this, where any two sets of vertices that look the same essentially have the same color. So what do I mean by look the same? Well, here, if I look at these sets, then they both correspond to this tree, this green tree here. So because they correspond to the same ordered subtree, they have to have the same color. However, if I look at this set of three vertices or this set of three vertices, they don't have to be of the same color because they correspond to different ordered subtrees. So here's really the point why we needed this kind of funny definition of an ordered tree. The reason is just I want to make this lemma work, and if I didn't put order, then I just wouldn't be able to make it work, because I could have a coloring where everything that looks like this is green, but everything that looks like this is orange. And if I didn't have order, then I would want them to look the same, but I can't force it. So that's why we need order. Okay, so we have this, which again essentially will allow us to assume that two edges that look the same, so they correspond to the same sort of forests, they have the same color. Right, so now what I'm going to do is follow the same pattern as before. So I want to show how to move from step J to step J plus 1. And to do so, I'll define an auxiliary coloring of a certain power of G. As following, I will color an edge UV of this power of G by a pair C and S, where C is a color and S is some ordered tree on L leaves. If there is a short C-colored L power of a path from a copy of S in the tree at U to a copy of S in the tree at V. And this may fail, and in that case, I will color the edge gray. Right, so again, I get exactly the same two cases that I had before. I either had a long monochromatic path, or I get many gray cliques. So long monochromatic path looks kind of something like this. I have a bunch of trees, and I have a way to walk from a tree or from the leaves of a tree S to a tree S in my next vertex, and again from a copy of S to a copy of S in the next vertex, and so on. But we may assume by the previous lemma that trees that look the same, that are isomorphic, are kind of interchangeable. So I can change this copy of S by this copy of S to get a power of a walk, which is what I was aiming for. Okay, so in this case, when I find a long path, I'm happy. Otherwise, I find my many large cliques. And then I claim that I can kind of easily find my next tree. What many cliques means is that I have something that looks like this. So a gray clique in my auxiliary coloring corresponds to a bunch of trees, such that there is no way of walking between one tree and the other. And then I construct this new tree. So I will take, let's say I want to make a tree at U, then I will just join it to each of the other trees in my clique. This will give me something of height J plus 1. And again, it will be the case that I cannot walk between two trees, because I cannot walk between two copies of S, because if the two copies of S are in different trees, that follows from the gray edges, and otherwise it follows from the assumption on the tree. So anyway, what this shows is that basically I can go, if I'm in a bad case, then I can go from step j to step j plus 1. And finally, here's a lemma. Maybe let's not read it exactly, but what it tells me is that this will not go on forever. If I have a tall enough tree, then I will not be able to satisfy this property that I cannot walk from 2 copies of S. So my tree is tall enough, I will be able to walk, and so yeah. So this means that I just cannot go on forever. So after at most some constant number of steps, I will be done and I will have reached my good case and found my power of a walk that I want. Right, so this is our proof. So hopefully, if I don't know how much these order trees made sense, but maybe you got something some more understanding from the powers of paths, and basically the ordered trees sort of allow us to use the same ideas, but for this more complicated case. So let's look at some open problems. So this is something I stated in an early slide. We know that the Size-Ramsey number of a path is somewhere between 3.75 times n and 74 times n. I mean, probably unrealistic to determine precisely or close to precisely what this is, but maybe something here is improvable. I would guess that maybe one can do something here. Right, and similar question for S-colors. So this was 2 colors. For S-colors, I know that the S-color Size-Ramsey number of a path is somewhere between S squared times n and S squared times log S times n. Would be interesting to know, I guess, which bound is correct, and I would guess that the upper bound is the truth or closer to the truth. Right. Now, I guess a more ambitious direction is to look at this conjecture of Rödl and Semrady. So they wanted to look at Size-Ramsey numbers of bounded degree graphs. So let's look at the maximum possible Size-Ramsey number of a graph on n vertices, which has maximum degree at most delta. It's easy to see that this maximum is the most n squared by results on Ramsey numbers. So they conjecture that you can do a bit better than n squared. You can do n to the 2 minus epsilon, and also n is obviously a trivial lower bound, so they conjecture that you can do n to the 1 plus epsilon. Now, this conjecture has been proved by Koyakawa, Rödl, Schacht, and Semrady. And they showed it for every epsilon, which is less than 1 over delta, which is kind of essentially best thing you can hope for if you're looking at random graphs as your examples. But this lower bound is open. And I mentioned this before, the best thing that is known is n times a small power of log n. Right, and finally, I don't know, maybe you want to just try to think about something explicit. So one thing you can look at is this grid graph. So this is I guess you can probably guess what it is. I maybe could have drawn it. But this n by n grid, it has n squared vertices and maximum degree 4. So it's kind of bounded degree graph. Would be interesting to determine, well, to say anything interesting about its Size-Ramsey number. So the best upper bound is this roughly n cubed recent result. And again, this comes from looking at random graphs, and this is essentially best possible if you're looking for random graphs. Right, so it's not even clear if the Size-Ramsey number of this should be linear in the number of vertices. I would guess that not, but I'm not sure. Right, and this is it. Thank you.
Well, thank you for the very nice talk. Let's just thank Shoham. Any questions? Or maybe just to clarify my previous question about the gray clicks.
Yeah.
So you found many gray clicks, but they could be far away from each other, or you prove guarantees they're close to each other.
No, I'm not assuming anything about where they are. I mean, I'm just like there are just a bunch of disjoint cliques, so that let me maybe try to go back.
But then when you clump two of them into another blob, you don't need them to be close to each other, do you?
Oh, wait. Right. So here are my gray cliques. So this is just guaranteed by what happens if I don't find a long monochromatic path. And I just claim that each of these cliques corresponds to a drawing like this, because each vertex was a clique and each gray edge is like a complete bipartite, so it corresponds to a clique. And that's it. That's all I claim. I claim that like if there are many of these gray cliques, then there are many of these disjoint like two-level blobs, and that's all I'm claiming at this point. Like I'm not saying that they're clamped or anything, but then just if I do another iteration this time on the auxiliary graph obtained by replacing each of these by a vertex, then again, if I find a clique, then it will correspond to a blob like this. So I just kind of get like these small structures together.
But many mean constant times n, right? Or...
Yeah, many means constant times n. I'm a bit lying here because you kind of want to always use, like you want to always use the underlying structure of G, which is an expander. But if you did it in this way, then your graph will shrink too much. So this doesn't quite work the way I presented it. But yeah, I mean, if you ignore this detail, then what you have is at the first step, you have a bunch of many blobs. Then at the second step, you have like many like two-level blobs. So you lost quite a few vertices, but you still have a constant fraction of them, and so on.
I see. Thank you. Any more questions?
Is there anything you can say about the constant factors?
I mean, short answer is no. Like it's really, really large. Because we just use Ramsey and iterate Ramsey type arguments a lot. So it would be really bad. And even in the step when we go from a walk to a path, then we lose quite a lot. So just a constant will be terrible. But I don't really have a bound, but I guess something like what you get for Ramsey numbers of hypergraphs maybe is similar to what we get.
Any more questions? So let us thank Shoham for a very nice talk again. Thank you.
Thank you.
Yeah, I guess the official